Good morning all, I am Tijin Thomas. I am going to give a small lecture on two-dimensional molybdenum carbide MXenes for gas sensing and hydrogen evolution reactions. And I completed my doctorate degree in science with specialization in sustainable processes from the Sustainable Process Department of Facultad de Ciencias Químicas, Universidad Autónoma de Nuevo León, Mexico. So coming to my topic. Major challenge of the present era is to provide a clean energy and safe environment. Burning of fossil fuels causes releases of hazardous gases into the environment. For that, proper monitoring of the emission of those gases is critical. And solution for this problem is to ensure air quality by monitoring them frequently. Gas sensors are used for this purpose, ensuring the sustainability. In addition, there is a need of clean renewable energy resource replacing the fossil fuels. And for this purpose, gas sensors are so vital. A gas sensor is a device which detects the presence or concentration of gases in the atmosphere. They are used for proper monitoring of the air quality. They work on the principle of variation in the electrical properties when a target gas molecule is exposed to the surface of the sensor. And these kind of sensors are generally known as chemi-resistive sensors. And they work on the principle that when a gas molecule is targeted onto the surface, they react on the surface of the gas sensors, making variation in the electrical properties, which can be measured quantitatively as the concentration and the type of the gases. The peculiar properties of these kind of sensors is that they possess high sensitivity, stability, repeatability, along with fast response and recovery times. Metal oxide semiconductors are well known for this kind of applications. Coming to hydrogen, they are known as the cleanest source of energy with zero emission of carbon. They can provide energy that 3 times gasoline or methane can provide. And cleanest way of producing hydrogen is from electro or photocatalytic water splitting. In this method, a water molecule is split into hydrogen and oxygen at the expense of energy. If the energy provided is electricity, it can be termed as electrocatalytic water splitting, and if the energy is in the form of light, that is sunlight or any artificial light source, this process is known as photocatalytic hydrogen evolution or water splitting. Here, a water molecule is split into hydrogen and oxygen in the presence of a catalyst, and this generated hydrogen is collected at the cathode and oxygen at the anode. And this collected hydrogen can be used as the fuel, which can be used as a fuel for the future, ensuring the energy. Coming to nanomaterials, nanomaterials are those class of materials which have a dimensions in the range 0 to 100 nanometers, and they can be classified into 0 dimensional, 1 dimensional and 2 dimensional depending upon the size of the dimensions. If all the 3 dimensions are in the nanoscale, these kind of particles are termed as 0 dimensional particles. If any 2 dimensions are in the nanoscale and the third dimension in a microscale, these kind of particles are known as a 1 dimensional particle, and the particles with only 1 dimension in nanoscale and the other 2 dimensions in microscale, they are termed as 2 dimensional particles. The advantages of using 1D and 2 dimensional 1 dimensional and 2 dimensional particles are they possess high surface area. That is, if S is the surface area of a 0 dimensional particle, 1 dimensional particles possess almost 1.3 times of surface area than a 0 dimensional particle, and a 2 dimensional particle possesses almost 3 times, that is 2.8 times the surface area of a 0 dimensional particle. So more the surface area, there will be more active sites available for the absorption of molecules, for which can enhance the gas sensing or hydrogen evolution activity of the material. Then I'm going to talk about a new class of 2 dimensional materials. They are known as MXenes, which are a 2 dimensional transition metal carbides, nitrides or carbonitrates. They are recently introduced by Gogotsi and group in 2011 in the Drexel University. And they have a general formula Mn plus 1 Xn or Mn plus 1 Xn Tx, where M can be an early transition metal, which can be titanium, molybdenum, or vanadium. And X can take the values, or X can be a carbon or nitrogen or the both. And Tx can be any functional group which is attached to the stoichiometry during the synthesis process, which can be a fluorine group, a hydroxyl group, or an oxygen group. And they are generally derived from a parent max phase, which have a general formula Mn plus 1 A Xn, and A can be a group 3 or group 4 element in the periodic table, and N can take the values 1, 2, and 3. One of the reasons for choosing molybdenum carbide MXenes as my research topic is that it is one of the least studied MXenes among the MXene group, because they possess excellent electrical properties. Their electrical conductivity is in the order of 2500 Siemens per centimeter, and also they possess a low hydrogen absorption energy, which is in the order of minus 0.69 electron volts, which make them suitable for the gas sensing as well as hydrogen evolution activity. Also, they find a lot of applications in all other fields of science. In our study, the MXene synthesis was attempted using, first we made the parent non-max phase. For that we used indium and molybdenum carbide as the precursors in the bulk form. They were crushed and grinded using a mortar and pestle and made a uniform powder mixture, which was transferred into a alumina crucible. And we have done calcination, or the heat treatment, which is again known as a solid state reaction, a physical method, inside a tubular furnace. We varied the synthesis temperatures like from 850 to 1100, and the reaction time was fixed for 2 hours. And we made a 3 sets of samples which was made at 850, 1000 and 1100 degrees Celsius. The obtained non-max phases was used as the precursor for MXene synthesis. Here we use the non-max phase in a phosphoric acid with the support of a UV light, and this UV light serves as the catalyst for the reaction, and we obtain a layered two-dimensional MXene after etching, followed by an exfoliation in DI water with the help of ultrasonic waves, and we obtain two-dimensional Mo2C MXenes. The structural characterization of the synthesized MXene and max phases were done using XRD, and in XRD we observed that the selective etching of indium is happening with the absence of indium peak in the XRD plot of MXene samples. As we can see in the XRD spectrum, these red plots are corresponding to the MXene samples and black plots corresponds to the max phases. We can see in the black plots there is a presence of indium sharp peaks which is absent for the MXene samples, which confirm the formation of MXenes. Also, we studied the morphology of the fabricated or synthesized MXenes, and all the samples were giving layered two-dimensional morphologies which confirm the formation of MXenes. Also, we have done transition electron microscopical studies, and we confirm that the interplanar spacing between the layers is increased when an max phase is transformed to MXenes. This is because of the selective etching of a layer, creating a vacant space in between the planes, which create an increase in the interplanar space. So this increase in the interplanar space also confirms the formation of MXenes. Then we have taken these MXene samples and deposited on different substrate materials to study the gas sensing performance. First, we used porous silicon substrates. We can see a porous morphology, and the deposited samples showed MXenes decorating the pores. The EDX mapping, that is electro energy dispersive X-ray diffraction studies, also confirm the uniform deposition of MXenes on the porosilicon substrate. Then we have compared the performance of the fabricated sensors by depositing MXenes on different substrate materials. First we deposited on glass substrate, then on a crystalline silicon substrate, and then on a porous silicon substrate. And we used carbon dioxide as the target gas. We observed that the sample prepared on a porous silicon exhibited better sensing performance within a range from room temperature to 250 degrees Celsius. Also, we varied the concentration of carbon dioxide. In all the three cases, we observed that the sensor fabricated on porous silicon exhibited excellent sensitivity when compared to the glass and crystalline. This may be due to the high surface area provided by the porous nature of the substrate. And a maximum sensitivity was observed at 250 degrees Celsius and 150 ppm of carbon dioxide, which was 25%. Then we have studied the influence of humidity on the performance of the sensors, and we observed that with the increase in the humidity, there was a corresponding increase in the sensitivity. And the sensitivity increased to 32% at 250 and 150 ppm of carbon dioxide concentration. This may be due to the interaction of water molecules in the sensing mechanism. Then we have calculated the response and recovery times for the sensor fabricated on porous silicon. We observed that for all the cases of all the concentration of carbon dioxide and all the working temperature, the response and recovery times were in the order of seconds, which was a great achievement of our studies because the previous reports were all in the order of minutes, so like 10 to 9 minutes, which was very difficult for the researchers to apply for the real life application. So in this research we could successfully fabricate a sensor which works so fast, like it can detect the sensing like the gas within seconds and recover within seconds. So this is a great achievement of our group for realizing a device like this. And in the case of high humidity, we observed that there was a delaying of the response and recovery. This may be due to the interaction of water molecules in the sensing mechanism. Then we have studied the performance of MXenes as an electrocatalyst. For that, we prepared electrocatalyst of MXene on a nickel foam. For that, we used 5 mg of the molybdenum carbide MXene powder in 25 microliter of isopropyl alcohol and 25 microliter of naphthalene, ultrasonicated for a period of 1 hour to make a thick slurry. And this thick slurry was deposited on a nickel foam and dried overnight to get a uniform deposited MXene on the nickel foam, which serves as the working electrode for the hydrogen emulsion reaction. For that, we used a 3-electrode system with platinum as the counter electrode, the prepared nickel foam based MXene sample or MXene on the nickel foam as the working electrode, and AgAgCl as the reference electrode in a 0.5 molar H2SO4 electrolyte, which is an acidic. And we have analyzed the performance of the fabricated electrode by plotting a polarization curve from the linear sweep voltammetry, which was done in the range 0 to minus 0.8 volts with a scan rate of 5 millivolt per second. And we observed that the sample synthesized at 850 degrees Celsius has exhibited the lowest over potential the value minus 138 millivolts at a current density of 10 milliampere per centimeter square, which is the lowest value for a molybdenum carbide MXene as per the report. And the corresponding Tafel slope was 41 millivolt per decade. This process was limited by a process known as Volmer-Hevrosky mechanism, which obeys the kinetics, or this system obeys the Volmer-Hevrosky mechanism kinetics. To understand the mechanism of the system again, we have done electrochemical impedance spectroscopy and we have plotted a Nyquist plot. And from this we calculated the charge transfer resistance, and which was in the order of 10.38 ohms, which is at the lowest for a molybdenum carbide MXene based electrocatalyst. And this system was equivalent to a modified Randall cells. So coming to the conclusions, we successfully synthesized molybdenum indium carbide non-max phases and prepared Mo2C MXene from these non-max phases for the first time using a HF-free method, which is a eco-friendly method of producing MXenes. Then we have fabricated gas sensors which detect carbon dioxide with fast response and recovery times in the order of 33 and 45 seconds at room temperature using molybdenum carbide MXene. And then we have successfully fabricated electrocatalyst with a lowest hour potential of minus 138 millivolt at a current density of 10 milliampere per centimeter square, which is the lowest reported value for molybdenum carbide MXene electrocatalyst. So thank you.